I would like to thank the organizers for inviting me to this conference honoring Eli in this beautiful city of Wrocław. We should be thankful to you, Eli, for many things, but I would like to single out your mentorship and support of young people. It has certainly made a big difference in my life, and I'm sure in the life of many other people. So today's talk is about spherical maximal functions, which we will define shortly what that means. This goes back to joint work with Detlef Müller more than a decade ago, and I would like to describe some of that, and then I would like to talk about newer developments. So there's also some work with Malabika Pramanik on seemingly unrelated issues, which in the end were ideas from that collaboration were applied to the Heisenberg group, and a very recent paper jointly with Teresa Anderson, Laura Kladek, and Malabika Pramanik. All right, so perhaps it may not surprise you that I don't really care so much about the Heisenberg group, but the problem is formulated on the Heisenberg group, but may be a model in more general situations. And so I'd like to just review notation on the Heisenberg group. So Heisenberg group is parameterized by n, and the Heisenberg group, or Hn, is of dimension d equal to 2n plus 1. We'll express many statements in terms of d rather than n. The group law is given by additivity in R2n and a twist in the last components. So we have xu dot y v is x plus y and u plus v plus a bilinear form in R2n, and that bilinear form is Q-symmetric and non-degenerate. So I would just like to emphasize that it doesn't really matter what J is for us, but in estimates we often want some uniformity in J, as J ranges over a compact set of Q-symmetric non-degenerate matrices. So then we have written down the convolution. We're going to deal with convolution operators. The explicit formula is here. So you may wonder what happens if we interchange F2 and F1. We get a similar formula, but the bilinear form changes its sign, and so that reflects the non-commutativity. Now, on the Heisenberg group, as everybody knows, of course, we have a group of automorphisms respecting the group law, and that's the dilation in R2n by t, and non-isotopic dilation by t squared in the center. And for a measure, we will denote a measure mu. We will denote by mu sub t the dilated measure adapted to scales t in the L1 normalization. Now, the object of interest is the maximal function, where we sup over the convolution of f with a measure mu dilated by t, and the real interest is for mu being in a supported in a hyperplane on the Heisenberg group. And the natural hyperplane might be the horizontal hyperplane, just R2n, but our interest is in stability of such an estimate when we change the hyperplane to a hyperplane nearby. Okay, so just to expand on that point, so we have here the natural subspace R2n cross 0, which is invariant under our dilation group. But if we change this to a different hyperplane, so we write this hyperplane as a graph of a linear functional over R2n, we get another subspace. We could put our measure there, and then from the dilation group. And now that subspace is not invariant under our dilation group. Okay, and so there's the stability question. Suppose we have a maximal function for a measure supported in R2n. We put this measure in a natural way on a tilted hyperplane. What happens with the estimates? Are the estimates still true, or do we get different estimates? Okay, so now just to repeat a phrase in Jim Wright's talk, we should ask ourselves what can go wrong and what should go right. And so there's really no reason that such an estimate is stable under perturbations. And so perhaps the very natural example is not the example that we're ultimately interested in, but an easier example. Namely, we just take the hyperplane R2n and we put the characteristic function of a ball on it. Okay, and then we dilate. Now, what is this, the maximal function associated to this measure? This is just a maximal version of the singular Radon transform in the paper by Geller and Stein. So the first example of a singular Radon transform, and here we have the maximal Radon transform. So the associated maximal function is bounded on LP for all p greater than 1. So why is that really the case? Well, the plane is invariant under dilation, and so it's very easy to dominate this maximal function by the associated Lacunary maximal function, simply by an obvious estimate. And what happens if we tilt this? And say we fix an x, and then we look at the associated hyperplane, which goes to x given by the convolution law, and then we dilate the measure. What happens is that this hyperplane will suddenly rotate because it's not longer invariant under dilations. Okay, so dilation on this hyperplane, this tilted hyperplane, not the tilt of in this case, but we start with a tilt here, and then we look at the Heisenberg translates of the tilted hyperplane. That's not invariant under dilation. And so if we look at the corresponding local maximal function in this case, we realize that it's very close to the spherical maximal function in Rn, or in Rd rather. What happens if you are at x and you look at a function which has a singularity at the origin, you could adjust your dilations just so that this plane eventually for suitable dilate hits the origin. Okay? And so that example is very much in the spirit of the spherical maximal function. And so what we see is that boundedness can only hold for p greater than d over d minus 1, exactly the exponent for the spherical maximal function. And now sort of standard methods from generalized Radon transforms show that indeed this maximal function is bounded for p greater than d over d minus 1. So this is necessary and sufficient. And if we use non-isotropic Calderon-Zygmunt theory on the Heisenberg group, we could extend the positive result to all dilations. Okay, so we do not have stability in this simple case. This is not really the case which is the object of this talk. What we would like to do is to replace the ball by the sphere, okay, which has been done, which has been investigated more than a decade ago, and I will just give the references in a moment. But we can think of the sphere, we could think of a surface with non-vanishing curvature, or measures which are localized on the sphere, so we have quite a bit of freedom there. Now, there are two different cases that I would like to single out. In the first part of the talk, I would like to review some of the older results which correspond to the measure in the horizontal hyperplane, and then I would like to discuss possible perturbation or non-perturbation result, whatever it might be. Okay, so this subject was started in a paper by Amos Never and Sundaram Thangavelu, who showed LP boundedness for some range, not quite the optimal range in the first paper. And they used methods from spectral theory or harmonic analysis on the Heisenberg group to do this. And then just a little bit later, there were two papers in 2004 in the Israel Journal of Mathematics, one by Detlef and myself, and one by Narayanan and Thangavelu, who proved a sharp estimate. And so the result will be that for p greater than the dimension -1 over d minus 2, we have boundedness. Okay, so this excludes the case of the Heisenberg group H1. Now there's quite a number of activity in the subject now, but I do not want to say anything about the Heisenberg group H1 today. So we can always assume, or mostly assume, that n is greater than or equal to 2, or d is greater than 3. So why is this result sharp, d minus 1 over d minus 2? You can think of a more trivial example where we do not have the Heisenberg convolution, but the Euclidean convolution, and then things simply happen in Rd minus 1, and we have the standard example in Rd minus 1. And that idea can be modified to also show that this example, that this result is sharp. Now, the proof of this result cannot be based on slicing, but it has to be based on, there's no way to slice this result on the Heisenberg group. Now, in the paper with Detlef, we actually considered a somewhat larger family of groups, Heisenberg type, or more generally, Métivier groups, but this is really not the issue in this talk, and we ignore this. And we came across already then this stability problem, what happens when we tilt the plane and we weren't able to prove a sharp result, or otherwise we weren't able to prove the sharpness of our result, which is mentioned here. So there is some intermediate range between the original paper by Nevo and Thangavelu and the sharp result, d minus 4/3 divided by d minus 7/3, but the sharpness was left open. Okay, I would like to talk about this paper with Detlef a little bit. And so in order to understand the full maximal function, we should first understand this local maximal function where we sup over t between 1 and 2. And one then hopes, and it is true, that methods from Calderon-Zygmunt theory can be used to put different scales together. All right. Now, the way we want to view things is to say that this convolution is something like a generalized Radon transform, and then we would like to prove smoothness estimates for this convolution. So in order to do so, we have to work with the right Sobolev space. But in the end, of course, we're just interested in LP estimates for the maximal function right now. We realize, of course, that the measure is compactly supported, and therefore we can assume that the function f is in a, say, wall of radius 1 near the origin. Once we have a good estimate for that, we can simply put estimates together by using the translations on the Heisenberg group. Okay, so but once f is localized, compactly supported, then we can think of Sobolev estimates in the usual way. All right, so now we would like to write this convolution as what we call a generalized Radon transform, and it is done here. So we realize that, of course, the sphere in the hyperplane has codimension 2, is a codimension 2 manifold R2, and so we like to write this Radon transform for a fixed dilation T as an integral over yv for fixed xu in the Heisenberg group. M should also depend on T, and we like to describe what this manifold is. Okay, so we need two defining equations. Of course, one equation should say that we are on the sphere, and the other equation should say that we are on this hyperplane. Okay, writing out these two equations leads us to these two inequalities that for two functions phi1 and phi2, phi1 is equal to 0 and phi2 is equal to 0. Okay, so that gives us the description of the convolution as a generalized Radon transform. Okay, so what we really want is we want to look at this generalized Radon transform, and we want to take the t derivative of order 1 over p plus a little bit and bound this in LP, and then by Sobolev embedding we are able to bound our maximal function. Okay, so the way we often get LP bounds is that we first prove an L2 estimate, and then we interpolate with some easier L1 estimate. And so let's focus for the time being on an L2 estimate. Okay, and for the L2 estimate, we have to differentiate 1.5 plus epsilon times. So the way one likes to estimate such a Radon transform is by dyadic decomposition, just decomposition in frequency space. And the way this is done is that we write out the Schwarz kernel of this operator as a conormal distribution. It's a delta function composed with a defining function, and we write out the Fourier integral for the delta function in R2 with two defining functions, and that gives us an oscillatory integral, and we take that oscillatory integral and divide it in dyadic pieces for large frequencies. Okay, so now what I've written here in the displayed formula is such an oscillatory integral where the frequencies are about 2 to the k, but I've written it in a way which is already rescaled. So the frequencies of size 2 to the k are written as 2 to the k sigma tau. Sigma tau are the two frequency variables which are now of size 1. Okay, so we think of sigma tau in this formula of a size less than or equal to 1, but the vector sigma tau is of size 1. Right? Okay, and so now to analyze this oscillatory integral, what we should check is that the basic assumption on Fourier integral operators is satisfied, namely that the conormal bundle for our manifold is what's called a local canonical graph, and harmonic analysts would say that the codimension 2 analog of the Fungsten rotational curvature condition is satisfied. Okay, so let's see what this condition is, which is a standard condition in the theory of Fourier integral operators. So the certain determinant of a big matrix ought to be uniformly bounded below. So this big matrix is sort of kind of misleading the way it's written. There is actually a big square matrix which is just one single entry. This mixed Hessian here is a d by d big square matrix, and then we add the gradients, the x gradients and the y gradients in the columns and rows. But we see that this square matrix now depends on two frequency variables. So in the Fungsten rotational curvature condition for hypersurfaces, we can simply get rid of the frequency variable by factoring it out for the determinant of this matrix, but in codimension 2 case we cannot do this anymore. So this is a function of the direction, if you want, in the normal plane for every point. Okay? And so it turns out, as you see, so we would like to evaluate this determinant on our manifold. Our manifold is given when phi is equal to 0, so the O of phi there is completely irrelevant. But when we are on this manifold, then this in fact degenerates. It becomes 0 when the dual variable to the sphere is 0. Okay, and so the standard theory doesn't apply, but one can analyze the behavior of this canonical relation, and it turns out that it is a folding canonical relation in the sense of Melrose and Taylor. And let me just explain what that means. Okay, so if we look at our conormal bundle, which is in the cotangent space of the x u variable cross the cotangent space of the y v variables, and we project this down to the cotangent space of the Heisenberg group in the xu variables. We call this projection pi L. There's another one to the other side. Then this map is not longer a diffeomorphism, not even locally. It's a fold. Now, what is a fold map? Well, if you think of a diffeomorphism, it's by a tautology, it's the identity. It's diffeomorphically invariant to the identity. But a fold is diffeomorphically invariant to something which looks like this, the identity in the first d minus 1 variable, and then you square it. So that's about the simplest degeneracy for a map that you can have. And so it turns out that the analysis of this map yields that it's a fold singularity. So you can write this down in a concrete way by parameterizing the normal bundle. And how would you parameterize it? Of course, you would solve your two defining equations, and they are easy to solve. They're solved here. Y2n is expressed in terms of the other variables, and the variable v is expressed in the other variables. So we parameterize it by xu, and then by the first two n minus 1 variables of y, and then we add the two frequency variables. We write out this projection. So what we have here in the last component is sigma times the gradient of phi plus tau times the gradient of phi2. So there should be phi1 there as a misprint. Phi1, the first one is a phi1, and the second one is a phi2. Okay, so we analyze this map, and we come the conclusion that it is a fold singularity, and the theorem by Melrose and Taylor tells us that unfortunately we lose 1/6 derivatives, which puts us immediately out of the range of the conjectured, or the true, in this case for lambda equal to 0, theorem. Now, in order to really understand better, we should not follow Melrose and Taylor, but we should use the Fungsten approach, understanding how to estimate fold singularities, and that approach is related to the idea of damping oscillatory integrals. So we say where this projection, which in some ways the determinant of this projection is some kind of curvature, where this curvature is small, we localize where this curvature is small, and we try to understand the dependence on the smallness of this determinant. Okay, so this is what's done here. In this integral that we had on the other slide, we simply localize where this determinant, namely approximately sigma, where sigma is small. Okay, so we look at the cases where sigma is 2 to the minus L, and for technical reasons, it is convenient or perhaps necessary to stop when L is k over 3. When L is k over 3, our cutoff will be the cutoff where sigma is less than 2 to the minus k over 3, but we'll just ignore this. So the Fungsten approach, which was expanded later in Shipio-Kokanya's thesis and a number of other papers with particular, maybe weaker conditions, it gives us that, our estimates are the optimal estimates in the non-degenerate case, namely 2 to the minus k d minus 2 over 2. So we gain d minus 2 over 2 derivatives, but then in dependence of this sigma cutoff, we lose a factor of square root of sigma, like square root of 2 to the L over 2. Okay? So as I said, again, that's bad news like before, but now something happens here. We're not really interested in this operator. We're interested in the derivative of, with respect to t, of order 1/2, or 1/2 plus epsilon. Okay, so what we normally do, if we can look at this integral, what actually happens. So everything in this integral depends on t, right? So we differentiate with respect to t. We bring down the power of 2 to the k. We lose 2 to the k for one derivative. We lose 2 to the k over 2 for a half derivative. But is that really true? Okay, so let's see what this integral really is. So this is integral of e to the I sigma something plus tau of something. But how does this depend on t? So this is tau of t squared times a defining function plus tau over t times something which involves this lambda. But if the lambda is equal to 0, then that's not there. So if that is not there, then you can simply change variables in this integral, maybe move the dyadic ring a little bit and suppress this tau. So if you differentiate with this power, this dependence on t will be a dependence in the symbol, which is completely harmless. Right? So, or you could say, well, this is when we differentiate t, we bring down 0 because we bring down the defining function. That's another way of looking at it. So that's not really there. So all you differentiate with respect to t is this guy. So we bring down the sigma, but the sigma is significantly smaller than 2 to the k. It's just 2 to the k minus L. So we gain 2 to the minus L. And so that really saves us here in the proof of our maximal theorem. So that's really the gist of this paper with Detlef. And I have written the estimates on the next slide. So we only we gain 2 to the k minus L. Now, if we have this perturbation, so if we are working on this tilted space, we get actually 2 to the k times the norm of the linear function. The linear function is small, this is small, but it's still 2 to the k. So this is really a non-stable situation. It's a non-stable proof for all that matters. And so, but then with this insight, it's rather standard to finish the proof of the theorem and to get, by interpolation arguments, to get to the LP boundedness of the local maximal function in the sharp range for p is greater than d minus 1 over d minus 2. It turns out that Narayanan and Tangavelu also proved this result on the Heisenberg group using completely different methods. Nothing about Fourier integral operators, but just a spectral theory on the group. But there is some commonality between the group if you analyze it, because what they indeed do is estimating a certain square function. And this square function has, of course, a derivative, implicitly at least, a derivative of order 1/2 plus epsilon with respect to t. Right? And it's that estimate that somehow in the calculus is better than it should be, and that's how they prove this theorem. Now, for the global maximal function, we use almost orthogonality arguments between the pieces, and so perhaps I shouldn't go there. Now, we want to ask now, what really happens if we perturb this situation? When we tilt this space, we do not have this clean result. This proof is highly unstable. So it turns out that the result is not unstable, and we get the same result even for the tilted case, which of course tells us that we have to come up with a different proof. Proof is highly unstable, but we need a different idea. So this is now more recent work with Anderson, Klardik, and Pramanik. If for the Heisenberg group Hn for n greater than or equal to 2, we get the sharp estimate for p greater than d minus 1 over d minus 2. Now, the LP boundedness of the maximal operator still follows from a regularity result, but it is no longer a good regularity result on L2. It is a regularity result on LP, and a regularity result on LP which cannot be obtained by some interpolation between L1 and L2. So we have to work with LP directly, and we'll see what that is. So if we have a good regularity result in LP, so P is now between 1 and 2, and so we want to gain d minus 2 over P prime derivatives. That's what we would get in the case of non-vanishing rotational curvature. But we don't have this, so we have to get this directly only for some p. We don't get it for 2, but we have to get it for some p in a range. And so once we prove this, then the effect of differentiating with respect to t is really the same as the effect of taking a gradient. So differentiating with respect to t 1 over p times gives us an additional effect of 2 to the k over p. And so if we are in the range of p where minus d minus 2 over p prime plus 1 over p is negative, then we have proved a maximal result for the local maximal function. Okay, and so we'll just for the time being concentrate on the local maximal function. Okay, so this regularity result that I want happens to hold for p less than 2 times d minus 1 over d, which I remember as the critical index for Bognor-Ries in d minus 1 dimension. So it happens to be that way. I'm not exactly sure why. Now, this regularity result is an estimate for the dyadic frequencies. The dyadic frequencies correspond essentially to a little Wood-Paley decomposition on both sides. And so it can be interpreted as a Biesov type regularity. It is rather easy. Well, it's a different type of mathematics is needed to combine the frequencies, but it's possible. And in fact, this type of result relies on Eli's ideas, namely the idea that the space H1 or BMO can be used to prove endpoint estimates. And using this idea, one can show the appropriate Sobolev results. So just you can combine the dyadic frequencies. You can actually do a little bit better. So instead of looking at the space LP, so you get the LP to LP Sobolev with d minus 2 over p prime derivatives in this range. You can do a little bit better on both sides. The square function in LP could be replaced. The little larger space on the left-hand side and a little smaller space on the right-hand side, which would make this theorem a little bit better, but let's not go there. So there's a paper with Malabika, Pramanik, and Keith Rogers in 2011, which sort of gives the general setup for this. But for the maximal operator, we are completely happy with the fixed frequency estimates. Okay, so this relies again on an idea of Eli's. So this was made explicit. What might be needed for estimates like this, but actually was looked at for different types of estimate in a paper with Alan Greenleaf a long time ago. And that paper dealt with not with LP Sobolev regularity, but with LP improving estimates. And what's special about this was that one of the spaces in the LP improving estimates involved the space L2. And so if you are in this case of an operator with a fold singularity on one side even, but here we have it on both sides, a curvature condition in the fibers so we fix XU and then we look at the canonical relation at the normal bundle over XU. What we get there is a cone, and if this cone has curvature, we look at this cone over the points where the rotational curvature degenerates, where it's 0, and then we get a conic hypersurface, and if this hypersurface has curvature, then we expect some improvement. So we at the time proved some sharp L2 to LQ estimates. And so that's the idea here too, but it was idea in the paper with Alan was based on, or was inspired by the situation for oscillatory integrals related to the Fourier restriction theorem. So we also have this type of situation, except we do not, the estimates are between spaces of different dimension, which is different here. Now the idea for the proof of our theorem now is to first use duality, and then for the dual estimate use Tom Wolf's inequality for decompositions of neighborhood of cones, which is now known as an LP decoupling estimate. Okay, so Tom Wolf's inequality was some years ago, 2014, dramatically improved for the best range. So Tom Wolf gave us the idea what the inequalities should be and proved them in some range. And the best range of these types of inequality was obtained by Bourgain and Demeter. All right. Now, for our maximal inequalities, we do not need the full range. And so let me go back to the last slide, just review those exponents that we had for both theorems. So we had d minus 1 over d minus 2 in the maximal theorem, which goes to 1 when d goes to infinity. And we had 2 d minus 1 over d for the regularity theorem, which goes to 2. Okay, and we need that the second exponent is larger than the first one. All right? And so one realizes that even with Tom's original result or the extension to higher dimensions of Tom's result by Waber and Wolf, this situation is already present. So we will not actually need, at least in sufficiently high dimensions, the full strength of the Bourgain-Demeter decoupling theorem, but we could use the old theorem. So that goes wrong when n is equal to 2, but I haven't checked. Probably n greater than or equal to 4, or perhaps even n greater than or equal to 3 should be okay. Do not hold me to that. Now there's an analogy to a previous result, which was jointly with Malabika, and this also concerned a codimension 2 situation, just the situation of curves in R3. Okay, so we have the operator f of x minus gamma of t dt, where gamma of t is equal to t squared t cubed. Say we go from 0 to 1 here. And would like to understand what are the best possible LP Sobolev estimates. And we know it cannot be better than LP to, or say LQ to LQ 1 over Q when Q is greater than 2. And it turns out that for some range of Qs, this is actually true. The best possible range is Q greater than 4. And so what we did, we used Tom Wolf's theorem to prove an estimate. If you just plug in the numerology of Bourgain-Demeter, then you get this result. And it also turns out that by an example of Dan Oberlin and Hart Smith, this is actually the sharp range. And so this proof inspired us to try the same in this situation. Another type of inspiration or a project with Malabika, which resulted in an unpublished manuscript, which we maybe intend to publish, is a variable coefficient version of this result. And we are in a variable coefficient version of this result on the Heisenberg group, at least for n equal to 1, if we don't care about the maximal function. I should say that maximal function estimates here in the spirit of the spherical maximal functions are also true, but there's a little bit of a discrepancy between this problem and the one in the Heisenberg group. And I said there is some activity going on, but I do not wish to comment more on that. So, what is the issue in applying a decoupling inequality? Okay, so what I would like to do, I would like to look at our operator. Now this is this operator RKL, where we localize in the frequency variables, and we say we are of distance 2 to the minus L to the degenerate surface. And now we would like to localize this in XU space to a small cube, so chi L x naught U naught. It's a small cube of width 2 to the minus L. Now, the contributions from different cubes can be easily decoupled simply because they're disjoint. Okay, so that's easy. The sum is dominated by the LP estimate, so we should just concentrate on such a cube. Now, what we would like to say is that if we look at the cone that was there before, we look at this sigma xu cone in the fibers, and we freeze it at this point x naught u naught. We would like to say that the Fourier transform of this object is essentially supported in a thin neighborhood of this cone. It should be a thin neighborhood of width 2 to the minus 2L. And it's very easy to see that it's essentially supported in a neighborhood of width 2 to the minus L. So the difference is between 2 to the minus L and 2 to the minus 2L. In fact, what I just did, I omitted the scaling. The scaling is, of course, we scale it up to 2 to the k, so the neighborhood in the scaled case should be really 2 to the k times 2 to the minus L or 2 to the minus 2L. So we have to somehow deal with that difference. Now, in principle, I think what could happen if we move this cone, this critical cone, which describes our curvature, inside this cube. So if, say, x naught, u naught is the center, and we move it around, it could be that the aperture of this cone changes. It could be that it changes by the amount of the diameter of this cube, by 2 to the minus L. Okay, and then the decoupling theorem would not work. I mean, we cannot let this happen. All right? And so perhaps the idea would be to change variables such that this actually doesn't happen. So in a particular coordinate system, this doesn't happen. Now, I don't think this is possible in a global sense, but changing variables may be possible at a particular step of the decoupling procedure. At some step, at some scale, changing variables may be possible. And in fact, this is the idea of the proof, that we use decoupling together with many changes of variables. Okay, so then we'll describe to you the basic decoupling step. So in this decoupling step, we have two scales which somehow correspond to the decoupling procedure. There's a big scale, and we think that we have a decoupled situation at scale delta naught, which is less than 1, maybe much less than 1, and we would like to go to a smaller scale. Okay, so think that we know that our Fourier transform in some sense is already supported in a neighborhood of a cone of width 2 to the k times delta naught squared, and we would like to go to a lower neighborhood. Okay, so this delta 1 should be significantly smaller than delta naught, but not too much smaller than delta naught. And what the condition is written here, and it is not so easy to explain quickly where this condition comes from. It comes from a technicality in the proof. But let's just say we can deal with this, and I give you the result. So let's now think of this point, the XU localization near the origin. Well, that's a translation, that's not hard. And let's think of the function be supported in a cube of side length delta naught, say centered at the origin. Okay, that we can also achieve. And now we would like to decompose this cube into smaller cubes of roughly cubes of side length delta 1. And I should think of this decomposition in frequency as corresponding to different parts on the cone. All right? And I also should think of the size of delta naught, when we take the Fourier transform, corresponding to a region on the cone which is of angular width delta naught. Okay, so it's not actually the full cone that we consider here, but just a region of angular width delta naught. And now there's a crucial condition. If we parameterize the relevant parts of our sphere by so x2n minus y2n is equal to g of x minus y in the first two n minus 1 variables. Okay, so the sphere is a graph of a function. This function g has non-vanishing Hessian. And I would like to normalize things such that at the origin, the derivative is equal to 0. The gradient is equal to 0. Well, that can always be done. But of course, it cannot be done universally. It cannot be done on all cubes. It can just be done on one cube. Right? But once a cube is decoupled, it can be done on that decoupled cube. Okay, so we do lots of changes of variables at every decoupling step. Okay, so now with this assumption that g prime of 0 is equal to 0, we can prove that the Fourier transform of this operator acting on a piece f nu supported in a small cube is essentially Fourier supported in a plate which comes up in the Tom Wolff decoupling theorem. And this plate would be a plate of size, well, 2 to the k is the frequency scale, but then it's of, this is multiplied with the plate of dimensions 1, delta 1, and delta 1 squared. Delta 1 squared in the normal direction to the cone. Okay, once we have this situation, we can apply our decoupling inequality. And so I have just not Tom Wolff's inequality, but in fact the Bourgain-Demeter inequality. And it says that the sum of the pieces is dominated by essentially the LP norm. P is the Stein-Thomas index for restriction in RD minus 1. The LP norm is dominated by, of the sum is dominated by the square function of the LP norms. Okay, so we go from L1, we gain over L1 to L2 in some sense, plus a negligible term. The negligible term contains what I say is essentially Fourier supported, but we just assume that all the negligible terms are easy to estimate. Okay, so that's the basic improvement here, and it relies, of course, on an LP estimate and not an L2 estimate anymore. Okay, so this basic step is now iterated. Okay, once you have decoupled, then you change variables to create the crucial cancellation condition, and then you iterate, and you end up with an estimate, which is where we take now a big cube. Function is supported in a big cube, and we divide this into cubes of size 2 to the minus L, or slightly larger, 2 to the minus L times 1 minus epsilon, and we write our decoupling theorem for that. Okay? In that decoupling theorem, if we have the little L2 decoupling theorem, we don't lose much. If we have the LP decoupling theorem, we just apply Hölder's inequality and we get a sharp result. Right? Now we look at the right-hand side of the decoupling inequality, which is, well, I'm sorry, I'm not done yet, but I will be in a moment. This is we look at the right-hand side. The right-hand side is very easy to estimate. And because it's not longer a sum, it's now the little LQ norm of the LQ norms. We estimate it by interpolation. For q equal to 2, we have the L2 result from the Fourier integral operator theory. And for q equal to infinity, we just estimate every piece. Now the function is supported on a set of diameter 2 to the minus L. So we gain that support in the L infinity estimate. That's a huge gain. That's 2 to the minus L to the power d minus 2. So that gain will help us put these estimates together and then get the right result for the LQ norm of this piece RKL. And then we sum in L, lose a logarithm, and we can finish the theorem. Now the final step, of course, would be, after we proved the local maximal function, to prove the global maximal function. And that step uses an LP version of Calderon-Zygmunt theory, because we're working with an LP estimate. So this is somewhat similar to papers by Tony Carberry and also myself a long time ago. But it's not that hard because we're dealing with a maximal operator, and we can use the structure of the maximal theorem. And then putting that together, we get the claimed result. All right, and now I can thank you for your attention.